This is lecture number 28 of the course AU 203 Statistics and Quality Control. In this lecture, we will talk about hypothesis testing, look into the definitions, what is null and alternative hypotheses, different types of error associated in hypothesis testing, and one-tail and two-tail tests. And then we will go into one of the method for hypothesis testing called critical value method or rejection region method. Okay, so the concept behind hypothesis testing is the purpose of hypothesis testing is not to find out the unknown parameter of a population, but actually to work out or make a decision about the two contradictory statements or claims about the parameter. So in hypothesis testing, we will be not interested in the value of the parameter, but actually we have two statements available for a parameter, and we are going to decide, make a conclusion, test that which of the statement is correct. And obviously we are actually talking about deciding about the parameter which is from the population, but obviously we can always take samples, and that gives us an evidence about the parameter. So based on that evidence, we are going to make a decision about these two statements. So these two statements or claims are called as null and alternative hypothesis. So we will see what these statements are. For example, let's say we are interested in the mean weight of all the bags of potato chips packed by a particular machine differs from the advertised weight of 50 grams. So here the parameter is the mean weight, and on the advertisement or on the wrapper of the potato chips, the weight written is 50 grams. So it's weight, what you call it, one of the statement is what you call it, that the mean weight is 50 grams. So that becomes your null hypothesis. And if we are going to investigate that the alternative hypothesis is either it is other than 50 grams, so that would be the two claims. And for example, here the null hypothesis would be that the mean weight is 50 grams, and we use H naught to represent the null hypothesis, and alternate hypothesis would be that the mean weight is other than 50 grams. So whether it could be smaller than 50 grams or it could be greater than 50 grams. So the purpose in hypothesis testing is once again the inferential statistics. In inferential statistics, we have already seen that we are interested in predicting the behavior of the population or the population parameter. And obviously, but here we are not interested in the estimate of the population parameter, but we are interested in making a decision about the two claims or two contradictory statement about the parameter based on the evidences given supplied through the samples. So logic behind hypothesis testing is if the sample data are consistent. For example, we have the sample data from the sample, and the data truly represent the null hypothesis. Null hypothesis is always status quo. So when we say that if status quo is correct and our sample data is consistent with the null hypothesis, then we are not going to reject the null hypothesis. So this is one of the possibility. Other possibility is if your sample data is not consistent with the null hypothesis, null and supportive of other statement other than the null hypothesis statement, what you call it, an alternative hypothesis, then we are going to reject the null hypothesis in the favor of the alternative hypothesis, because we have substantial evidence from the sample that the null hypothesis is not correct. So in hypothesis testing, we could be either the data would be consistent, so that consistent with the null hypothesis, then we are not going to reject the null hypothesis. If data is inconsistent, then we are going to reject the null hypothesis. Then we have to believe in the alternative hypothesis. So this is the logic behind hypothesis testing. Okay, so the null hypothesis is we used denoted by H naught is actually a statement or a sort of a prior claim or a status quo that is initially assumed to be true. So this is actually your null hypothesis. So which is your anticipation about the parameter. That statement is called as the null hypothesis, and the hypothesis testing is a procedure of making a decision about whether the null hypothesis is correct or not, and that decision to be made based on the sample evidence provided through sample data. So obviously the other contradictory claim that would be called as alternative hypothesis, and HA is a symbol to represent that hypothesis. So that would be just an opposite or other than the null hypothesis. Whatever the statement other than the null hypothesis would be called as an alternate hypothesis. So null hypothesis will reject in favor of alternative hypothesis only if the sample evidence suggests that the null hypothesis is false. So if the sample evidence does not strongly contradict, and we will look into what does it mean by strongly contradict, but later we will see how we can say that the evidence is strong or weaker evidence when you will go into this p-value method probably in the next lecture. So if our sample evidence is not in supportive of the null hypothesis, then we are if the sample evidence does not strongly contradict H naught, then we will continue to believe in this null hypothesis. So the two possible conclusions from a hypothesis testing would be either we are rejecting the null hypothesis, or we are failed to reject the null hypothesis. So these are the two possibilities that may arise from hypothesis testing, whether you are going to reject H naught because you are going to reject H naught because your evidence is not in favor of null hypothesis, then you are going to reject H naught. Or even though your null hypothesis was incorrect, but you don't have the enough evidence and you fail to reject H naught. So these are the two possibilities. So we can write that the conclusions of hypothesis testing are most of the time usually presented in this form. We are going to reject the null hypothesis. H naught is the null hypothesis in favor of an alternative hypothesis because of the sufficient evidence in the data. So if your data supports and have a sufficient evidence, then you can say that we are going to reject the null hypothesis. So one of the possibility of this hypothesis setting to reject H naught, or you can say you are failed to reject the null hypothesis because of insufficient evidence in the data. And the same thing happens in the jury trial, where the defendant is assumed innocent before start of the trial, or a prior claim is always that the defendant is innocent. So that would be the null hypothesis, and obviously the contradictory claim of the null hypothesis would be an alternative hypothesis that the defendant is guilty. So for example, if you reject H naught, it means the defendant is innocent. That is your null hypothesis. So if you reject that defendant is innocent, and once it is not innocent, then it would be considered as guilty. And we can only do once we have sufficient evidence. The same thing is in jury cases sometimes happen is your null hypothesis that your defendant is innocent, but you don't have insufficient data, and you are failed to reject that the defendant is innocent. So these are the two possibilities that always happen, and the same happens in this hypothesis testing. Okay, so the question about there, you're dealing with two types of statements. One is the null hypothesis, which is about something about a parameter, and another contradictory claim is obviously other than the null hypothesis. Your hypothesis statement, whether it's a null or alternative hypothesis, there are possibilities like in most of the cases in statistics we will be specifying the value of a parameter. For example, if you say the mean height of women would be 66 inches, so this is your prior claim, and then you can investigate whether the mean height is greater than 66 or less than 66 or other than 66. So, or it could be you are interested in investigating or making a decision about whether the standard deviation of their height is equal to 5 inches or other than 5 inches. Or if you are interested in finding out the proportion of defective in a manufactured item, whether it is the prior claim is that only 0.1% are defective. So if this is your prior claim, that could be one of the hypothesis statements. So one of the way by which you can write down just like the same as estimating the characteristics of a population, what you call it a parameter. So in all that parameters, you will be interested in the it could be any of the statement. Or sometimes you need to specify the difference between the two corresponding parameters of two populations or more than two populations. So let's say, for example, if you have the male height and the female height, and you are investigating whether the male height is greater than the female height or male height is less than the female height. So it could be such a statement could be one of the possibilities, possible statement of hypothesis. Or sometimes you need to specify the type of the distribution that best describes the population. So let's say you are investigating the height of the female students, and you are interested in whether the sample data has enough evidence that the height of the female undergraduates is a normal distribution. So in this way you will be actually making a decision about the model which you want to suggest for a given or for any characteristic from the population. So these are the three possibilities by which you can write down your hypothesis statements, or it could be anything, any statement which is one statement which is a status quo, that would be called as a null hypothesis, and other would be an alternative contradictory to the null hypothesis, that would be called as an alternate hypothesis. Okay, so obviously there are a possibility of making error in a sense that you have made a decision based on the sample evidence, and the decision is that you have rejected the null hypothesis, even though it was in reality it was true. So the null hypothesis was true, but you have rejected the null hypothesis. It means you have made certain error. This error we call it a type 1 error. The second possibility is you are failed to reject the null hypothesis when it is false. So you're essentially your null hypothesis was false, and your hypothesis testing came through from the evidence of the sample data that which doesn't have that supportive evidence. So as a decision maker, you are failed to reject that null hypothesis when it was when it is false, then it would be called as type 2 error. So look at this matrix where we have the true state of the nature, whether the null statement is true, or other possibilities your null statement is false. You measured, you perceived, and you make certain decisions based on your sample evidence. So your decisions could be two decisions: either you reject your null hypothesis or you fail to reject, because other than this is not actually a possibility in hypothesis testing. So if your true state of nature is your null hypothesis is true, and you reject the null hypothesis even though it was true, it means you have made an error. So that error is called as type 1 error. So type 1 error, keep in mind, always rejecting the null hypothesis when it is true. So your decision is that you are rejecting the null hypothesis when null hypothesis is true. It means you have made an error, what you call it a type 1 error. Let's say if your null hypothesis is true and you are failed to reject your H naught. So it means you are accepted your H naught. It means you have not made any error. Other possibility is if you are failed to reject your null hypothesis given that or such that the same thing you have used in your conditional probability when your null hypothesis is false. If this is the situation, then you made an error, what you call it a type 2 error. So type 2 error is fail to reject. Your decision is to fail to reject the null hypothesis. So you are only dealing with either rejecting the null hypothesis or you are failed to reject the null hypothesis. So your interest lies with the decision about the parameter. That is what your status quo is. So either you are rejecting your status quo or you are failed to reject your status quo. So when your null hypothesis is false, which is not true, so it means the right thing is if it is false and you have rejected your null hypothesis, then you made no error. But if you are failed to reject your null hypothesis when it is false, then you made an error called type 2 error. And we use Greek letter alpha to represent the type 1 error. So alpha is just a probability. Probability is always a number between 0 and 1. So the type 1 error is when you make a type 1 error, and the probability of making a type 1 error is called as alpha. Or type 1 error means you are rejecting your null hypothesis when null hypothesis is true. So always remember, if you remember this table, then you can easily find out which error is type 1 error or which error is type 2 error. So always one of the possibility is rejecting your null hypothesis when it is true. Then you make an error, what you call it a type 1 error, and that probability is represented by some number which is between 0 and 1, that is called as alpha. Alpha could be 5%, alpha could be 10%. Whereas the type 2 error is you are failed to reject your H naught when your H naught is false. H naught means your null hypothesis. So the probability of failing to reject H naught when H naught is false or such that H naught is false, that would be called as, that probability would be for making a type 2 error is represented by a letter beta. So this is exactly the same thing in this trial of when your true state of the nature for a defendant is the defendant is innocent. And if the descendant is innocent and your decision is to reject innocence, so if you reject innocence, it means it is a guilty. So that is actually called as type 1 error. And not guilty and you considered them innocent, then again you made an error called type 2 error. So it is, if you remember this, you can easily find out for this situation as well, or for any other situation where you have two claims. One is your status quo claim, or where your prior claim is what you call it a null hypothesis, and other is when you have an alternative hypothesis, which is the contradictory claim. Okay, we can represent this type 1 and type 2 error with this flowchart as well. Let's say you start your decision and you are going to decide about whether your null hypothesis to be rejected or not. If you reject your null hypothesis, if it is yes and your null hypothesis was true, so it means you have rejected something which was true, it means you have made an error. This is called as a type 1 error. If you didn't have, if your H naught was not true, then you made a correct decision because you have rejected your null hypothesis which was not true and you made a correct decision. Or if you're investigating your null hypothesis is rejected, and if it is not been rejected, and then if null hypothesis is true, and you haven't rejected it, means you made a correct decision. Or if you H naught was not true and you actually failed to reject H naught, it means when H naught was false, where H naught was not no means H naught true means no means H naught is false, and you are failed to reject H naught, then you made an error called type 2 error. Okay, these null and alternative hypothesis. So whenever you are talking about null hypothesis, you always represent your null hypothesis in the form of an equality. Equality means, let's say my null hypothesis is that the mean value is equal to some particular mean mu naught. It means the mean height or mean weight or whatever the parameter of interest is, it is some fixed value. So what we're going to do is this null hypothesis is represented by means of an equality. So we cannot say mu is greater than mu naught or mu is less than mu naught. So we always specify the null hypothesis as an equality. So that the probability of making a type 1 error can be controlled at some specific value. So this is, we will see it's later once you will see the things, both hypothesis, null and alternative hypothesis on the same graph in the next lecture. An alternative hypothesis, you don't need to have an equality, but you need to have an inequality, or it could be either one-sided or two-sided, depending upon the conclusions to be drawn. For example, if the objective is to make a claim involving statements such as greater than, less than, or exceeds to, or superior to, or inferior to, or so forth, then it is called as a one-sided alternative hypothesis. So alternative hypothesis is not necessarily be an equality. It should be inequality as well as whether greater than or smaller than. For example, let's say this is a null hypothesis, which is an equality, whereas this alternative hypothesis that your mean value is less than this mu naught. So and then there is certain probability associated, and probability is represented by the area under the curve on a distribution. Let's say this is the sample distribution. So mean is actually the population parameter, mu naught, and x bar is the sample distribution. So if this area is let's say 5% area, so if there is certain critical value of the sample mean where you have a threshold or a significance that you are going to reject your null hypothesis in favor of alternative hypothesis, because once your sample mean is going to lie in this region, it means your mean value is obviously not the same as the mu naught. It would be other than mu naught, or here in this one-tailed test, if it is less than mu naught, so the less than mu naught could be in this region, could be here, could be here, could be here, but there is some critical value. If it is less than that, we can make a decision that we call it a sufficient evidence. For example, if your sample mean, its critical value lies such that you are in this region, then you are going to reject your H naught. Or other possibility would be if your sample mean is not the same as mu naught, but if it is greater than mu naught, but how big in greater that or how strong the evidence from your sample mean is that it is not your sample mean is other than mu naught. So it could be here, it could be here, or if it is somewhere here in this area, which is our threshold significance. So if our sample mean would be coming into this region, we are going to reject our null hypothesis. So since either it is smaller than or it is greater than, or we call it to be a one-tail test. So the two-tail test would be just if your claim of an alternative hypothesis implying no direction, whether greater or small, but it says your alternative hypothesis says your mean is unequal. So you can say on both sides, instead of the whole alpha is divided into two parts, alpha by 2 and alpha by 2. So the total area would be representing certain probability. If your sample mean is lying in that area, you are going to reject your null hypothesis. So this is called as a two-tailed test because it could be either less than this critical number or it is greater than this critical number. In either case, your null hypothesis is not correct, so you are going to reject your null hypothesis. So in formulating this one-sided hypothesis, we must remember that we are going to reject the H naught is always a strong conclusion. So for example, this could be here, or if it is, let's say, somewhere here, then we have some very strong conclusion that it is much greater than this critical number, and so we can strongly reject our null hypothesis. But if it is somewhat here, very much close to this point, or somewhat hovering around C prime or around C here, then we can reject, but we don't have a strong evidence of rejection. So this usually happens is once we are talking about area, then we cannot specify, but once we specify the p-value, which we'll learn later, then we can easily specify that we have some sufficient evidence of rejecting the null hypothesis. Because you have only two decisions, either to reject your null hypothesis when it is true, or you have failed to reject null hypothesis when it is false. So these are the only two possibilities that are available in hypothesis testing. Okay, now look into the method, what you call it, a critical value method or a rejection region method, which is actually based on the fixed probability of making a type 1 error, or your alpha value is something given in the problem. So these are the following are the steps which okay, so these 7 steps in order to solve problems from this critical value method or rejection region method, what you call it, the one of the method, and second method is the p-value method, which we'll do it in the next lecture. For example, the first step is to pick the parameter of interest or define the variable, whether it is a mean value, or is a standard deviation, or a proportion defective, or a difference of mean value, or difference of proportion, or whatever it is. The second step is to state the two statements which are contradictory claims, null and alternative hypothesis. In the third step, you need to look for the distribution of the test statistics. Test statistics is always from a sample data. And obviously assuming that the null hypothesis is true. So and the fourth step is state the type of the test, whether it is a one-tailed test depending upon the given problem. You have to or based on your statement of your alternative hypothesis, you have to choose the type of the test, and obviously your significance level to be selected or chosen, or it is given in the problem. That is actually the probability of making a type 1 error. Then you choose an appropriate test statistic. For example, if your distribution, it depends upon the distribution. So most of the time we are dealing with the normal distribution, or any distribution which is close to the normal distribution, then the test statistic would be a z value. and we have to establish the critical region based on the significance level or the probability of a type 1 error. So based on that, if your test statistic have a sufficient evidence from your test statistic that whether it is in this region of rejection or if it is not in the region of rejection. So if you need reject null hypothesis, if your computer test statistics is in the critical region or in the alpha region where your test statistics lie in that. And then obviously in the last step you have to make some scientific or engineering conclusions. Okay, so best understood once we solve a problem by employing all these steps. For example, each year trainees throughout the country sit in a test, and over a period of time it has been established that the marks can be modeled by a normal distribution with mean 70 and standard deviation 6. So this is something predicting about the mean marks. This year it was found that the trainees from a particular country didn't perform well as expected, and the marks of the random sample of 25 trainees from the country were scrutinized, and it was found that their mean marks were 67.3. Does this provide evidence at a 5% significance level that the trainees from this country didn't perform well as expected? So from this question, I mean, obviously in examination you have not mentioned whether this problem belongs to hypothesis testing or not. But here the statement, does this provide evidence at this 5% significant level that the trainees from this country didn't perform well as expected, because their expected score is 70, and if they are performing less than 70, it means their performance is not up to the mark. So this is about making a decision about population through a sample statistic, and the sample statistic here is a mean value which is given. Okay, just follow it. The first step is to define the variable, or what is the parameter of interest for you, where let x represents the marks of a trainee from the particular country, and that's a random number which can take any value. It could be 80, it could be 60, any marks a particular trainee can take. So we are assuming that their population mean marks is mu, which is which is unknown here for this particular population, and we are assuming that the standard deviation has not changed. It means your x is the marks of trainee, which is normally distributed with mean mu and variance 6 square, because standard deviation is 6, so the variance is 6 square. So this is the first step. In the second step, you need to define your alternative and null hypothesis. So as I told you that null hypothesis is always formed from an equality. So equality here is the mean marks equal to 70, and this is the presumption that the trainees have performed as expected. So their expected score is 70, or mean score is 70 over the years. So this is your status quo, or this is your prior claim. And your alternative or your contradictory claim is at a particular year the performance of the trainees are not up to the mark and their mean score come out to be less than 70. So here the sample statistics represent that the mean mark is 67.3, which is less than 70. So keep in mind, I cannot say mean marks is greater than 70, because the performance expected is less than their expected performance. So we always need to take an alternative hypothesis, mu is less than 70. So this always comes as a one-tailed test. In the third step, you need to state the distribution of the test statistic according to the null hypothesis. So the test is to be carried out based on the sample mean x bar. X here is population parameter, where x bar is the sampling mean. So considering the distribution of the sample mean, the distribution of the sample mean would For a sample size of 20, we can say that it's normally distributed with the mean mu and variance sigma square over n, which we know from our sampling theory that this would be the sampling distribution of the sample mean. So if your your null hypothesis is true, then your mean would be 70. If it is not true, then it would be less than 70. So that is something, the step number 3. So we need to look for the test statistics based on the sample data. And in the 4th step, we need to look for the type and the level of the test. So here alternative hypothesis is one-tailed test. So we are interested in the critical region, some critical value based on this 5% level of significance that brings up a criteria by which we can reject our null hypothesis. Okay, in the step 5, you need to decide on your rejection criteria. We know the test statistic, which is a sample mean would be 67.3. So at 5% level of significance, we work out the z value. Z value is x minus mu over standard deviation, and here standard deviation is sigma over under root 25. So you come up with the z value from this calculation. You come up with minus 1.645. So if your z value is less than 1.645, then we can safely reject our null hypothesis in favor of alternative hypothesis. So we will be sure that the mean marks are less than 70. We have a strong evidence, we can say that. So what we do is we calculate the required statistics. The test statistics value of the test statistic is 67.3. So we calculate its z score corresponding to 67.3. So at this 1.645 is based on 5% significance level. When your area under the curve of a normal distribution curve is less than 5%, then your z value is minus 1.64. So this is something to develop your rejection criteria. So now you calculate the test statistics based on your 67.3 value. Just substitute x bar 67.3, then you come out to be minus 2.25. So you can see that your critical value is minus 1.645 and your test statistics, your evidence is minus 2.25. So it is well below this value of your critical value. So you can see on the mini tab, or for example, if you calculate the area under the curve when your x score is 67.3, then this would be the area under the curve. And if you calculate the z value, so z critical value of the z is minus 1.645 when your area is 5% area on the normal distribution curve. And your sample statistic z value comes out to be minus 2.25. So it is well below this 1.645. So once it is well below, then you can say that you have sufficient evidence from your sample that you can reject the null hypothesis that the average score is 70. It is so in favor of an alternative hypothesis. So this is the conclusion that you are going to draw, that your sample statistics suggests that from this 5% area, so you are lying your z statistics value based on your sample data of 67.3, that your z value is less than minus 1.645, then you can safely say that you can reject the null hypothesis in favor of an alternative hypothesis. So here the mean mark of a trainee for a particular country are less than the expected. So your claim that your expected marks is 70 is not true, and your alternative hypothesis is correct. So this is how we can do that, and I will show you later about how to do it in this Excel as well, Minitab as well. Okay, so how we can do the same thing on a mini tab is, we know the problem is we have to go onto this test tab and basic statistics, and then here you need to go to this one sample Z test. So for example, what we are interested in determining whether the mean of a sample differs significantly from a specified value when the population standard deviation is known. So in this case, standard deviation is known. We just click on that. So you came up with this. You have two possibilities: one or more samples in column, or summarized data. For example, this time we have data is summarized, so that the sample size is 25 and the sample mean evaluated is 67.3, and obviously the standard deviation 6 is known, so you need to perform your hypothesis test, and your hypothesized mean is your, which is actually your null hypothesis is 70, where mean value is 70. And options here is your confidence level is 95%. It means your significance level is 5%. So 5% is that critical value. If on your normal distribution, if your data would be, your sample test statistic would be lying in that region, you are going to reject your null hypothesis. So alternative hypothesis here is your mean is less than your hypothesized means or your null. This is your alternative hypothesis. So you just click on OK, and just click on OK. By doing that, you come up with this on the session window. If you look at this session window, this is a one sample Z test, and test of mean mu is 70, which is your hypothesized value, or alternative hypothesis is that mu is less than 70. So and your assumed standard deviation is 6, and your sample size is 25, and your mean value is 67.3, and standard error is sigma over under root n, which is you can 6 divided by under 5, which would be 1.2, and you estimate the Z statistics, which is minus 2.25, and its critical value we have already seen is 1.645. So we can see that our mean is 67.3, and the upper bound for that mean value is 69.27. So we can do it with the p-value, which we will do it later, but this time in this lecture our critical region is less than based on the test statistics, its Z value comes out to minus 2.25, and its corresponding value of X bar would be 69.27. So we can see here corresponding to minus 67.3 is there, and 1.645 is there. So 16.4 corresponding, it would be the small value. So minus 2.25 is much smaller than minus 1.645. So we can say that its lower bound is going towards 0, and its upper bound is going up to 69 point something. So which is don't need to go into that, just look at the Z value. Here Z value is minus 2.25, that is estimated from this mini tab, and you can see on the mini tab this Z value is minus 2.25. Or we will see in this p value, which is less than the 0.05, then it means you can reject your H naught in favor of an alternative hypothesis, and you can here decide that based on this test statistical sample evidence that your mean value is not expected as 70, it is less than 70. So this is how we can do it in and we can plot these graphs to get the probability distribution plots. So let's say if you want to review that, for example, the Z value, the standard deviation for 1 and Z score, and you are interested in calculating this left probability for 0.05. So if you're interested in, you can easily find out the value of area is 0.05, where Z value, critical value is minus 1.645, and our test statistics suggests the Z value is minus 2.25. So it means it is in the rejection region. So you can reject your null hypothesis in favor of an alternative hypothesis, and you can visualize the probability distribution as well. Okay, we stop this lecture.